All right, so in this lesson we're going to start looking at the nature of waves and sound. And so the first thing to point out about waves is there are some terms and features that we use to describe waves that are important to note and important to know. One of those terms is that we call the crest being kind of the high point of the wave, and I call the trough the low point of the wave. In the case of what we call a transverse wave here, the crest is up, the trough is low. We'll look at what's called a longitudinal wave and kind of describe what's going on in terms of a longitudinal wave here in a second. We have wavelength, which is the length of one wave, and there's actually three different ways you could conceivably measure wavelength. You can measure crest to the next crest, you can measure trough to the next trough, or you could measure the 0 point from crest going to trough all the way over to the 0 point from crest going to trough. In each one of these cases, one complete wave is included in there. We have what's called amplitude, which is the height of the wave off of the 0 point. And so these are kind of some terms and features to know about waves when we talk about them. So how do frequency and period relate to one another with waves? We've already seen this relationship when we looked at simple harmonic motion or the circular motion. Basically what frequency is, it's a measure of how many waves pass by a specific point during a given second or a specific amount of time. It's measured in hertz. 1 hertz is 1 inverse second or 1 wave per second. So if you had a wave that had a frequency of 60 hertz, that'd be 60 waves passing by a location every second. Period is the time it takes to complete for one complete wave to pass by a location. Again, period is the inverse of frequency. So if you have 60 hertz or 60 waves per second, that means it's a 60th of a second per wave. So if period is 1 over frequency, frequency is 1 over period. That relationship works for waves as well as our simple harmonic motion. So let's look at wave speed. And so if we have two waves in the water, or two waves with wavelengths of 2 meters pass by a buoy in a second, how fast must the waves be moving? Well, wave moves 4 meters in 1 second. So we have this buoy, and look at how the buoy is moving. So the easiest way to calculate that would be wavelength times frequency gives you speed. And if we look at the units, meters times 1 over seconds gives you meters per second. So we do have an equation which relates wave speed to wavelength and frequency. That V equals lambda, which is the symbol for wavelength, times F, the symbol for frequency. This is what I call the wave equation. Anything that follows the pattern, or this is one of the things you look at to determine is something a wave or not. So the wave speed is related to both the frequency and the wavelength. So the other thing to kind of point out about waves is there's two main types of waves that we come across. One is a transverse wave. So here the waves are moving this way away from the person's hand. So these waves are traveling through the slinky or spring this way. But if we looked at any individual part in the spring, it's moving up and down, perpendicular to the motion of travel of the wave. So the wave's moving to the right, but the slinky itself is moving up and down. That's an example we call a transverse wave, that the motion of particles in the medium that the wave is traveling through is moving perpendicular to the direction that the wave is actually traveling through. One thing to point out about most waves is that they have to travel through some medium that has particles that allows the wave to travel through that medium to transfer that energy. Second type of wave is what we call a longitudinal wave. In a longitudinal wave, the wave is traveling to the right, but the individual particles are moving back and forth this way. So you get areas of compression and areas of expansion. In a longitudinal wave, the compression really acts like the crest, and the expansion really acts like the trough. A good example of a transverse wave would be an ocean wave. A good example of a longitudinal wave is actually a sound wave. If you look at what's happening to the particles of air as sound travels through it, you see there's areas of compression and expansion, and that this is how sound travels through air. So it's kind of a quick overview of some waves. What we'll look at in the next lesson is how waves travel through different types of mediums. We'll look at a string first and look at how waves travel through a string.